As I said, my name is Martin Bouckley. I just want to thank you all for coming. Thank you all for coming to watch this talk. I'm just going to be talking about how TrueAllele can be an efficient workflow and how you can compute first and then ask questions later. So, as you may be aware, sort of a bottleneck when it comes to reviewing STR data. With automation and robotics and things like that, it can be relatively fast to generate your STR data, putting it through your CE and then separating out the data there. But where the hard step comes in is when you have to look at that data and then you have to decide what are we actually going to call alleles. So you've got your stochastic thresholds and those sort of things, anything that's in a stutter position, anything like that, all those rules that you've got to go through before you can say, yes, I can analyze this data. Then it comes to actually analyzing the data, where you're going to be inferring these genotypes and then calculating all of your match statistics. So how can you get this to be faster? Well, simple way to be doing this is to be using TrueAllele and integrating that into your workflow. So your first step is going to be identical. You're going to be generating the data exactly how you would. But rather than looking at the data after that step, what you're doing is you're putting it into the TrueAllele software, and then it's going to be analyzing it before you ever look at the data. It's going to be inferring these genotypes for you. So by the time that you look at the data, you've already got some preliminary match results. You've got match statistics against references, against other pieces of evidence that you can be taking a look at before you see the data. So what does the TrueAllele casework look like? What we have here is the view station on the left, and that is what the analyst is sitting down in front of. And then all of the heavy lifting, all of the calculations, everything like that is done elsewhere on the database server so that you're not tying up the resources of your computer. You take minutes to set up your request, and then it takes minutes on the server to calculate those genotypes and get you results. And as I was saying, the database server there, that is the one that is going to have everything stored on it. So all of your data that gets uploaded to the database server, those interpret match is actually in the same box. Those are the things that are going to be picking up and solving those requests for you, storing them back onto the processes that are in the database server, and then you're sitting in front of your view station, you can pull those requests and all those answers down from that server. So rather than having to, let's say, tie up those resources, you're able to put that elsewhere and keep working on your machine doing other projects. So with this workflow, let's say you've got your plate data that you're then going to be analyzing with the TrueAllele software and actually in a module called Analyze. And all this is doing is quality checking your data. It's going to be quantifying the peak heights for you, and it only flags problems. Anything that's going through the software and it's fine, you don't even have to review. The computer's doing that automatically for you. So if you have a 96 well plate and there's only 2 things that fire and there's a problem, you only then have to look at those 2 pieces of data to make sure that everything is going to be okay. If a ladder didn't track properly and you've got other ladders there, you can ignore the one ladder and use the other ones. So this is when it comes to asking the questions of that data that you now have. It took maybe 10 minutes to analyze your data. And this step, asking the questions of it, takes seconds. So here, this is just an example of a 3 unknown question that you ask of the data. And it's just a generic question to ask. If it's a single source sample, or if there's only 2 unknowns in a sample, the 3 unknown is still going to be able to pull out those genotypes for you. It's not going to affect it that you've assumed that there's 3 people in there when in actuality there's less. And the same thing if there's 4 or 5. You're still going to be getting the genotypes there that are going to be giving you the information. Those very low-level 4 and 5 person minors, chances are you may not pull those out in a very quick screening, but then you could have a look at them later on if you needed to look more in-depth at them. So the computer solved all of those genotypes for you. It separated out a 3-person mixture into 3 independent genotypes, and that's the answers that it provides for you. And each of those genotypes is going to be assigned a mixture weight, and from those genotypes, you can compare that to evidence, you can compare that to references, and that's when you can calculate the match statistics and the likelihood ratios. And rather than you having to calculate these match statistics, it's the computer that's automatically doing that for you. It's automatically going through every single sample that you've put in there that you would like it to look at, and doing evidence to evidence and evidence to reference matches, and assigning a weight to these in the form of a log likelihood ratio. And this is just what TrueAllele looks like. The key part of this is, no matter what step you are in the process, you can always go back and have a look at your data in the form of those raw electropherograms. So if you're in your reporting stage and you've already got your log LRs and you still want to see, does this make sense with my data, you can always go back and look at it. It's always going to be there for you. And this is before you've asked any questions of it if you need to. Once it's done solving, and as say each genotype gets assigned its own mixture weight, what you can see here is a simple 70-30 two-person mixture that it was able to separate very easily. And this is the genotype that came from it. What we're seeing is that the blue bar is your evidence genotype that's been inferred, and the green bars are the references that it's comparing it to. You can think of the lighter green bar on the right there as a non-contributor to the sample, and the darker green as a contributor to the sample. So when it comes to match statistics, if someone is a non-contributor to that sample and you're doing an evidence to the reference match, you can expect to get a negative log likelihood ratio or an exclusionary statistic giving weight to saying this person really is not in this sample. And the positive blue bar that we're seeing there is the dark green in relationship to the blue genotype, and you would get a positive log LR score for that because it's saying that that person is in the data. And these are just some of the visual user interfaces that we have. It's very simple to become accustomed to. We do trainings. I personally help with the trainings, and people are able to get a hold of it within a day or so. It's very user intuitive. But how does this all relate to actual cases? So what we have here is, it was in California, and a gang moved in, and they started terrorizing the neighborhood, and within the span of about 10 days to 2 weeks, they had robbed these 5 places, increasing in violence. They were starting to hurt the people who they were robbing rather than just stealing things. So they wanted to get answers quickly, and that's why they sent the data to us. We received these 12 evidence items 1 week, completely separate from any references, and as you can see there, 5 different scenes and overall 12 evidence items, the counter, the safe, the keys, things like that. It's low-level amounts of DNA, and I'm going to be getting to the DNA slide later so we can see how low-level this actually was. But we started processing that evidence immediately. We didn't need the references because when TrueAllele is solving and separating those genotypes, it's doing it completely independent of anything else. It calculates the genotypes, and then later it compares it to the references. You don't need references in order to process your samples. And what you can see, you've got your 5 victims and your 5 suspects, and once we had those, we loaded them in and compared them within seconds. It had log LRs calculated for us. And this is what one of the pieces of data look like. So we can see that first contributor with human interpretation, it's not going to be a problem to take a look at. But when you start going down to that second contributor and the third contributor, stochastic thresholds and things like that are going to start to mean that you may not be able to call any peaks there. You may have to call those inconclusive, and the person of interest may be that second and may be that third contributor. But with TrueAllele, being it's a probabilistic genotyping software, we don't have to use those thresholds anymore. We're able to use all of the data that you produce, and as you can see, it's good data. There's peaks there. We want to be able to use it, and that's what we're trying to get to. So how does it explain this data? And what this is it's just the most probable answer for each of those individual genotypes. So the 13, 14, to assign the blue bars there, the 16, 18 would be the middle second contributor, and the third contributor at the bottom is the 17, 20. Now, it's not just trying out the best answer saying, yep, that looks right, we're just going to stay with that. It's trying out hundreds of thousands of different possibilities. So let's say for the second contributor, it wanted to try out a 14, 18. We're not saying that's not possible. It may not be the best explanation of the data, but it's still going to try it out for you, and it's going to assign a weight to that genotype, and that's what we can see here. You have your probability distribution for each genotype, and this is going to happen for each person at each locus. So for these, there's 3 individual probability distributions for these 3 people at just this one locus. And as you can see, the most probable one was that 1618. So it might make the most sense, but that's not saying that it's the only explanation of the data. We have the 1418, it assigns some probability to, and there's actually possibilities outside of the ones we're showing here that it tried out. It just said this really doesn't fit the data at all, so we're not going to be assigning it a high probability. It's going to be down there at like 1/10% or something like that. So when we've actually inferred all of these genotypes, then what do we do? And on the left there, that's where we have all of the items. And each one of those you can think of as an evidence genotype that we're going to compare to these 5 suspects. And the blue numbers there are the log LR values of these match statistics. So for the 4s up here, we're saying that it is 10,000 times more probable than coincidence that it matches suspect 5. Same thing with the 6 and the 11, just a 1 followed by 6 or 1 followed by 11 zeros. Just easier to display it this way rather than having huge numbers on the screen for you. So what do you do once you've got these results? You've got these matches before you've ever had to see your data. you can see your data at the same time as you saw that match statistic of 1 million to someone. So then you can start to prepare a case report. And this is just the language that we found is the easiest to convey to a layperson. And I don't know how many of you were at Jay Caponera's talk at the workshop earlier this week, showing how easy it can be to present this in court to the layperson. Just saying a match between the evidence and the suspect is 553 million times more probable than a coincidental match to an unrelated black person. And the reason that we can say it's a match is because we're separating out those genotypes. So we're separating them out and comparing one individual to another individual, and that's what we can say that it's a match. And you can see at the bottom there, in Forensic Magazine, this is just an article outlining why we chose this language and why it's easy to convey to a jury. Now, you've got these answers. How do you know that these answers are accurate, and how do you know that you want to present these answers in court? Well, TrueAllele has been extensively validated. These are just the 7 peer-reviewed published validations that involve TrueAllele. And what you can see, the top 4 in a lighter blue, those are the lab synthesized data. Those are going out all the way to 5-person contributors, all the way down to 200 picogram samples. So really trying to get any kind of sample that you can see in your lab and seeing how TrueAllele works with it. And then right in the middle here, with Susan Greenspoon and Virginia, this was done completely independently of Cybergenetics. So it's not just Cybergenetics that's validating TrueAllele anymore. There's labs that have taken this on board, and they're using it, and they're validating it themselves, and they're taking it to court. The bottom 3 here, these are casework samples. So these are the dirty ones. These are the ones that are going to be harder to interpret, but these are still going out to 4 and 5 contributors, the same as you would expect with the lab samples. And this is just an example of what the genotype database can look like with one of the studies that we've done. So this is what you would expect to see when you're comparing thousands of different genotypes together, and then you can get the distribution across the x-axis there. Now, on the blue side, these are matches that you would expect to have. It's a contributor distribution. Anything in there blue, and we're saying that the average is a very strong match statistic of about 1 followed by 17 zeros. So when the 2 items are matching, we're seeing that they're matching very strongly. And if it's a non-contributor, the red bars there, we're seeing that they're not matching, and we're actually able to give a weight to how much we can exclude that person. So it'll be a 1 divided by 1 followed by 24 zeros. So a very strong exclusionary statistic. We're not just saying that we don't know if the person's in there anymore. We're saying, no, this person isn't in there. And Kern County is actually one of the labs that's taken this on board. So they took the TrueAllele software, and within a year, with the support from Cybergenetics, they were able to be completely live and completely automated. So within a year, with our help, they were able to get everything up and running. And what they do is very simple, similar to what I've been talking about here. They generate all their data. They don't look at the data. They've got requests automatically set up. And what they're doing is they're setting things for 5,000 cycles with the MCMC. And they are screening all of their data before they ever see it. So they can set something up before you leave work the one day, you come in the next day and you've got your match results before you've ever had to do anything. Much more efficient than spending hours looking at data before you can start to compare it to anything. So how do they do these database matches? And these are the things that are going to be automatically done by the TrueAllele database servers. You don't have to tell it to match anything, it's doing that automatically. All you need to do is say, where do I want to look for these matches? And at the top there, we can see that it's within case. So you've got one case there, multiple different items, and we can see that there's strong log-likelihood ratios assigned to those. With the 4 that are checked there, it ranges from a 7 to a 15. So a 1 followed by 15 zeros is a very strong match between 2 pieces of evidence. These are those inferred genotypes that we were talking about before, not a reference sample. And then between cases, if you want to see, let's say you have, like the example that we saw earlier, a string of robberies or a string of cases that could be connected, but you're not sure, this is a very easy way to see if the same person contributed to those samples. And these are just results from screening. You can look into the data further by sampling more, and it's going to give you a more accurate answer because it's been able to look at the data for longer rather than just a quick screen. It's like glancing at something or actually reading it. You're going to have a better answer when you actually read it. We are actually having a webinar this Thursday. It is just trying to explain the likelihood ratio, drop in, drop out, how we model for those sorts of things. But if you have any questions, I'd be more than happy to answer them for you. If you need any more information, we have our Cybergenetics website and the YouTube page. Well, thank you all.